All right, let's review stuff from yesterday. So, let's talk about what a strong acid is and a strong base. So, for example, hydrochloric for a strong acid, and potassium hydroxide for a base on there. Why are these strong acids and strong bases? What happens to these guys when you put them in water? They completely dissociate. 100% dissociation. That is the distinguishing feature of a strong acid and a strong base. 100% dissociation. They fully dissolve. All the H's come off the Cl's. All the K's come off the OH's. 100% dissociation. It all fully dissolves in water. That was a part of it. By the way, this generates a heck of a lot of heat when it does this too. There's an expression about adding acids to water. About like when you're mixing water and acids, because it's really exothermic, so it gives off a lot of heat. So they say, do what you oughta, add acid to water. And the reason why is, so it generates a lot of heat. So if you have a lot of water there, it has molecules to absorb that energy. But if you put the acid in first and then add the water, it generates a lot of heat fast, what happens? Yes, you have an explosion. You instantly vaporize the water, which causes acid to shoot up out of the flask and potentially hit you in the face. Yes. It's very bad news. So you actually if you actually will drop acid in too in these water samples, what you actually see you'll see little puffs of water vapor as it goes into these strong acids. It's pretty freaky.
Are you going to demo it?
I suppose I could. Yeah, I suppose not right now. This second, I don't have any handy, but I could do that. Just drop. All you see is little puffs of vapor when it goes in. It's kind of neat. Okay, weak acids and weak bases. So, for example, hydrofluoric acid is a weak acid, and ammonia is our weak base we talk about a lot. What makes a weak acid weak? What about it? Yeah, it doesn't dissociate well. We only get a few of our H plus ions. They're going to break away. And what does it actually make when in the water? It doesn't just say H plus. What's it turn into? H3O. So we're going to create hydronium, H3O. That's really what makes an acid an acid. Production of hydronium ion. Weak base, what's going to happen there? When we drop a weak base in water, what happens? It mixes, yeah. But what else happens? What happens to the water? Yeah, we get hydroxide to form. So we get only a few hydroxide to form. Because remember, what makes a base is it's a proton acceptor. So NH3 strips off a hydrogen from water to turn into ammonium, NH4, leaving behind hydroxide ions. Some of you guys in the homework may have got to a point where, how come when I did my work, I wrote my equilibrium expressions for the strong acid and strong base, how come on the worksheet key it says none? Now here's the reason why you don't do equilibrium expressions for strong acids and strong bases. It's because they are so incredibly product favored. It's such a forward reaction with 100% dissociation. It's not really an equilibrium reaction. It's just a one-way reaction. It's so product favored we don't consider it equilibrium. It's all the reactants get converted to products. So that's why you just put none. It's not really equilibrium. So speaking of which, the real goal of today is to figure out this, hydronium ion concentration and hydroxide ion concentration. So let's look at how we can figure that out for different types of acids and bases. So start off with a strong acid. We'll say we've got 0.200 molarity hydrochloric acid. I want to know the hydronium ion concentration. What's that? What's our hydronium ion concentration? How are we going to figure that out? What? It turns out for these ones we actually don't have to use Ka, and exactly. You'll see in just a second. It relates to what the next one we will have to use Ka, but not for this one. Let's look at our reaction first off. This might help us out. So we got HCl, and what are we adding it to? Water, H2O. We put the equilibrium arrows, and we just talked about how it's really not truly at equilibrium. It's really so product favored that we're not going to have any reactant left. And we get chloride and hydronium ion. Remember that this splits apart to combine with the water to make H3O, and we're left with that chloride. Just for fun, let's put in our conjugate pairs for this. What do we call HCl? Acid. Then what is chloride? Yeah, it's our conjugate base. Proton donor, proton acceptor. And then what do we call the water? Base. And H3O, conjugate acid. Proton acceptor, proton donor. So again, what we want to know, what is going to be our hydronium ion concentration over here? If we have 100% dissociation, what's going to be that concentration? It is the same. That's right. The concentration of HCl, after it reaches equilibrium, after this reaction stops, is now the concentration of hydronium. Why? 100% of this turns into these guys. For every 1 mole of HCl, we get 1 mole of H3O. Does that make sense? It's like the coefficients, yeah. This completely dissolves, so yeah, it equals, it's the same. It's 0.200. And because of that, chloride concentration is also that. For every 1 mole of HCl, we get 1 mole of H3O. So if we've got 0.2 moles or 0.2 molarity HCl, we're going to have 0.2 molarity hydronium. Does that kind of make sense? Why we don't have to do anything for this? It's just, it all turns into product. No reactants is left behind, so it all turns into product. So these are the easy ones. So when you guys get to the homework, what you need to do is, there's no calculation you have to do, but you have to explain it. You have to be able to explain why this number and this number are the same. Okay, now we'll get on to Ka. We're going to use Ka. We're going to use Ka when we have our weak acids. So let's do our weak acid one. We are going to have .200 molarity hydrofluoric acid, HF. Same question. What is the hydronium ion concentration? So let's write our reaction again. HF combined with water in the liquid state. And again, our products are going to be similar. We're going to have fluoride ion and hydronium ion, both in aqueous solution, both dissolved. So these are truly ones at equilibrium here. So these ones we do have to set up an equilibrium expression and everything for this. So let's do that. Set up an equilibrium expression here. We'll call it Ka because it's an acid. The A is for acid. What's going to go on top? Yeah, F and our H3O. Or that's multiplication there. And what goes on the bottom? Just HF. Because water's in the liquid state, we only use least restrictive state, which is aqueous. Okay. So, next thing we do, we can look up Ka. We'll do that in a second. But we want to figure out the concentration of these guys. At equilibrium, we have the initial concentration. What do we have to use? Icebox. I guess it's on the board, so yeah, we're going to use ice boxes. So we're set up our ice box. We got our reactant, HF. And we don't have to include water because it's not an equilibrium reaction. We'll have our F minus and our H3O. Get my ice box set up. I'll start filling in what we know. I'll let you get those set up. Okay, so what do we know? Yeah, we know initially we got 0.200 moles HF. How much of this do we have initially? 0. So we got that down. We know we can put our change factors in, right? What's this one going to be? Minus x, because it's got to go down, right? Minus x, how about these ones? Yeah, these will both be plus x. Okay. We don't have these values, but in a way we do know the equilibrium value. Does anybody know what it's going to be? It's not going to be 0, because this one is, it's a weak acid, yeah, so this one won't be 0. It's going to be our 0.200 molarity minus x. Right? Because that's how you got that its equilibrium value is going to be. It's going to be this value minus whatever that value is. And because these values start out at 0, we know that they just equal x. These guys just equal x because you're just adding that amount. So I know there's a lot of x's in here, but we actually have enough information just about to do this. Now, we can start plugging this stuff into the equilibrium expression with the help of this table you guys got picked up. This table's got, on the back side, a bunch of Ka and Kb values, some equilibrium values for different acids and bases. So we go to hydrofluoric acid and find an equilibrium value, Ka value, of 6.7 times 10 to the negative fourth. So that's our Ka value. So we can put that down. And we can now set up our equilibrium expression. What's going to go on top? So products over reactants, so it's going to be x times x, or x squared. I'm going to put x times x for now, just to illustrate some stuff here. Then what goes on the bottom? 0.200 minus x. So you have two ways of going forward at this point. One way is really a lot simpler. This x value, because this is such a reactant-favored equilibrium expression, remember reactant favored versus product favored, bigger than 1 versus smaller than 1. This is super, super reactant favored. You're not making much product at all. We actually say this x value down here is negligible. We can cross it off. We get rid of that. It's so small, it's negligible. You can even make a little note there. So small. Whoops. I spelled that wrong, and then I corrected myself and spelled it. I spelled it right, and I corrected myself and spelled it wrong. Anyways, it's so small. You could actually solve this with leaving x in. Anybody know how you do it? You know how to do it. What do you do? Oh, no. If you didn't eliminate x. Yeah. Something close to that. Anyone ever heard of the quadratic before? You can use the quadratic to solve it. Now, I'll tell you, you can do it with a quadratic. What you're going to find is that when you do the calculation, you compare it to this way. When you figure in sig figs, it's the same answer. So that's why we eliminate x. It's so small, it's insignificant. Yes? Yep. For these ones, yeah. So we can solve for it. So we got 6.7 times 10 to the negative fourth equals x squared over 0.200. Get rid of that x. Multiply both sides by 0.200 to get x squared by itself. And we get x squared equals, you guys get 1.34 times 10 to the negative fourth. You didn't get that? Did you get 0.000134? That's the same thing. Just in non-scientific notation. So I'm going to do a lot of this in scientific notation just because it's easier to write stuff. And then we take the square root, and you get .0116, and that is your hydronium ion concentration right there. So that's how we get the hydronium ion concentration, the thing that really makes an acid an acid. Yes? You use iceboxes when you're dealing with weak acids and weak bases. When you're using strong acids and strong bases, you don't need to at all, because those ones really aren't at equilibrium. Which brings me to the strong base. we have 0.150 molarity sodium hydroxide. And I want to know this time, what is the hydroxide ion concentration? Remember, hydroxide is a thing that makes a base. Hydroxide production in water. So we can write our little reaction here. Sodium hydroxide plus water. And what do we get on the other side? We get sodium ion and hydroxide ion. And our water just stays water. Remember, that's a spectator. Doesn't participate. So again, my question is, what is my hydroxide ion concentration? It's the same, yeah. Because all of your sodium hydroxide, it dissociates into those guys. So our hydroxide ion concentration equals 0.150 molarity. It stays the same. All the sodium hydroxide comes apart, so the concentration before, for every 1 mole of sodium hydroxide, you get 1 mole of hydroxide, therefore the concentration is the same. Again, on the homework, you don't need to do any calculations, but you do need to explain why this actually works this way. You gotta talk about it. No. If you can explain out what goes on in like a sentence or two, that's fine. Okay, let's do a weak base one, and then I'll turn you guys loose. Weak base. We say we have 0.150 molarity NH3, and I want to know what is the hydroxide ion concentration. So now we have to write the equation for these ones for sure. NH3, combine it with water. What do we get? We don't get nitrogen. You get NH4 because remember the bases are proton acceptors. So it's going to pick up a hydrogen. And then what else do we get? Hydroxide. Hydroxide ion. And let's just for fun put our conjugate pairs on here because it's a good thing to know how to do. What's this one? Base. What's this? Acid. Okay. What do we call this? Yeah, that's our conjugate acid. It's the conjugate acid to NH3. And then hydroxide, conjugate base. You don't have to write the conjugate acid, conjugate base stuff when you do all these problems. I'm just doing it as a good review, okay? That's so, like when you guys do the homework, you don't have to do all that. What I need to see is this. I need to see your equilibrium expression. And what's that going to look like? NH4 and OH over NH3. There's our expression. And now it's ice time. Again, we don't include water because it's not part of the reaction. Okay. What can we fill in? 0.150. And then what goes in here? Zeros. What's going to go here? Minus x. Plus x. Plus x. Yep, 0.150 minus x. And here? X and x. So we got our icebox filled in. Now we got all of our information we need, so we can just go get our value off the table. So we go to the table of K values for weak bases. We see that, okay, we got pyridine, methylamine, and ammonia. Ammonia is 1.77 times 10 to the negative fifth for its Kb value. And now we can start plugging numbers in. We got x and x, which we can just turn to x squared. It's going to be x times x. And at the bottom, we can go ahead and just put a little line through this x right here, indicate it's negligible, and just write 0.150. I would like to see you guys crossing it out, including that, because in the future, you guys will do some reactions where you can't fully get rid of x. So it does come up, like nothing in here, but like in future chemistry, that could come up. So I just want to throw that out there that it could become an issue later on. So it's good, it's just good practice. Okay, now we can just solve for x. So isolate x by itself. I believe you should get 2.66 times 10 to the negative 6 equals x squared. Square root everything. Is it the negative fifth? Yeah, I think. Let me verify. I got negative 6 still. Yeah, just double check the calc. Just double check how you entered it in there. And your final answer? Oh, you put in scientific notation? 0.00163 or 1.63 times 10 to the negative third. And that equals your hydroxide ion concentration. That's it. That's how you do weak acids, weak bases, strong acids, strong bases. We got our hydroxide ion concentration and our hydronium ion concentration. Tomorrow, we're going to actually learn what that means, what we can use those for. Again, hydroxide and hydronium are what makes an acid and a base and a base, and we're going to connect that to pH. What pH is, what pH truly is. We talked about it as a measure of how strong an acid or base is. Now we're going to learn what it really is actually measuring to figure that out, how that's quantified. You need a calculator tomorrow that can do logs. Absolutely. No logs, no problems.